Chapter 14. The Fire Below. In the summer of 1971, a young geologist named Mike Voorhees was scouting around on some grassy farmland in eastern Nebraska, not far from the little town of Orchard where he had grown up. Passing through a steep-sided gully, he spotted a curious glint in the brush above and clambered up to have a look. What we had seen was the perfectly preserved skull of a young rhinoceros, which had been washed out by recent heavy rains. A few yards beyond, it turned out, was one of the most extraordinary fossil beds ever discovered in North America. A dried up waterhole that had served as a mass grave for scores of animals: rhinoceros, zebra-like horses, saber-toothed deer, camels, turtles. All had died from some mysterious cataclysm just under 12 million years ago in the time known to geology as the Miocene. In those days, Nebraska stood on a vast, hot plain very like the Serengeti of Africa today. The animals had been found buried under volcanic ash up to 3 meters deep. The puzzle of it was that there were not, and never had been, any volcanoes in Nebraska. Today, the site of Voorhees' discovery is called Ashfall Fossil Beds State Park. It has a stylish new visitors center and museum, with thoughtful displays on the geology of Nebraska and the history of the fossil beds. The center incorporates a lab with a glass wall through which visitors can watch paleontologists cleaning bones. Working alone in the lab on the morning I passed through was a cheerfully grizzled looking fellow in a blue work shirt whom I recognized as Mike Voorhees from a BBC Horizon documentary in which he had featured. They don't get a huge number of visitors to Ashfall Fossil Bed State Park. It's slightly in the middle of nowhere, and Voorhees seemed pleased to show me around. He took me to the spot atop a 6-meter high ravine where he had made his find. It was a dumb place to look for bones, he said happily. But I wasn't looking for bones. I was thinking of making a geological map of eastern Nebraska at the time, and really just kind of poking around. If I hadn't gone up this ravine, or the rains hadn't just washed out that skull, I'd have walked on by and this would never have been found. He indicated a roofed enclosure nearby, which had become the main excavation site. There, some 200 animals had been found lying together in a jumble. I asked him in what way it was a dumb place to hunt for bones. Well, if you're looking for bones, you really need exposed rock. That's why most paleontology is done in hot, dry places. It's not that there are more bones there. It's just that you have some chance of spotting them. In a setting like this, he made a sweeping gesture across the vast and unvarying prairie. You wouldn't know where to begin. There could be really magnificent stuff out there, but there's no surface clues to show you where to start looking. At first, they thought the animals were buried alive, and Voorhees stated as much in a National Geographic article in 1981. The article called the site a Pompeii of prehistoric animals, he told me, which was unfortunate because just afterwards we realized that the animals hadn't died suddenly at all. They were all suffering from something called hypertrophic pulmonary osteodystrophy, which is what you would get if you were breathing a lot of abrasive ash. And they must have been breathing a lot of it because the ash was feet thick for hundreds of miles. He picked up a chunk of grayish, clay-like dirt and crumbled it into my hand. It was powdery but slightly gritty. Nasty stuff to have to breathe, he went on, because it's very fine but also quite sharp. So anyway, they came here to this watering hole, presumably seeking relief, and died in some misery. The ash would have ruined everything. It would have buried all the grass and coated every leaf and turned the water into an undrinkable grey sludge. It couldn't have been very agreeable at all. The Horizon documentary had suggested that the existence of so much ash in Nebraska was a surprise. In fact, Nebraska's huge ash deposits had been known about for a long time. For almost a century, they had been mined to make household cleaning powders like Comet and Ajax. But curiously, no one had ever thought to wonder where all the ash came from. I'm a little embarrassed to tell you, for he said, smiling briefly, that the first I thought about it was when an editor at the National Geographic asked me the source of all the ash, and I had to confess that I didn't know. Nobody knew. Voorhees sent samples to colleagues all over the western United States, asking if there was anything about it that they recognized. Several months later, a geologist named Bill Bonnichsen from the Idaho Geological Survey got in touch and told him that the ash matched a volcanic deposit from a place called Bruno Garbage in southwest Idaho. The event that killed the plains animals of Nebraska was a volcanic explosion on a scale previously unimagined, but big enough to leave an ash layer 3 meters deep, some 1,600 kilometers away in eastern Nebraska. It turned out that under the western United States, there was a huge cauldron of magma, a colossal volcanic hotspot which erupted cataclysmically every 600,000 years or so. The last such ep- the last such eruption was just over 600,000 years ago. The hotspot is still there. These days, we call it Yellowstone National Park. We know amazingly little about what happens beneath our feet. It is fairly remarkable to think that Ford has been building cars and Nobel committees awarding prizes for longer than we have known that the Earth has a core. And of course, the idea that the continents move about on the surface like lily pads has been common wisdom for much less than a generation. Strange as it may seem, wrote Richard Feynman, we understand the distribution of matter in the interior of the Sun far better than we understand the interior of the Earth. The distance from the surface of Earth to the middle is 6,370 kilometers, which isn't so very far. It has been calculated that if you sunk a well to the center and dropped a brick down it, it would take only 45 minutes for it to hit the bottom. Though at that point it would be weightless since all the Earth's gravity would be above and around it rather than beneath it. Our own attempts to penetrate towards the middle have been modest indeed. One or two South African gold mines reach to a depth of over 3 kilometers, but most mines on Earth go no more than about 400 meters beneath the surface. If the planet were an apple, we wouldn't yet have broken through the skin. Indeed, we haven't even come close. Until slightly under a century ago, what the best informed scientific minds knew about Earth's interior was not much more than what a coal miner knew, namely, that you could dig down through soil for a distance and then you'd hit rock. And that was about it. Then, in 1906, an Irish geologist named R. D. Oldham, while examining some seismograph readings from an earthquake in Guatemala noticed that certain shock waves had penetrated to a point deep within the earth and then bounced off at an angle, as if they had encountered some kind of barrier. From this, he deduced that the earth has a core. 3 years later, a Croatian seismologist named Andrija Mohorovičić, who was studying graphs from an earthquake in Zagreb, when he noticed the similar odd deflection, but at a shallower level. He had discovered the boundary between the crust and the layer immediately below, the mantle. This zone has been known ever since as the Mohorovičić discontinuity, or MOHO for short. We were beginning to get a vague idea of the Earth's layered interior, though it really was only vague. Not until 1936 did a Danish scientist named Inge Lehmann, studying seismographs of earthquakes in New Zealand, discover that there were two cores, an inner one which we now believe to be solid, and an outer one, the one that Oldham had detected, which is thought to be liquid and the seat of magnetism. At just about the time that Lehman was refining our basic understanding of the Earth's interior by studying the seismic waves of earthquakes, two geologists at Caltech in California were devising a way to make comparisons between one earthquake and the next. They were Charles Richter and Benno Gutenberg. Though for reasons that have nothing to do with fairness, the scale became known almost at once as Richter's alone. They were nothing to do with Richter either. A modest fellow, he never referred to the scale by his own name, but always called it the magnitude scale. The Richter scale has always been widely misunderstood by non-scientists, though it is perhaps a little less so now than it is early days when visitors to Richter's office often asked to see his celebrated scale, thinking it was some kind of machine. The scale is, of course, more an idea than a thing, an arbitrary measure of the Earth's tremblings based on surface measurements. It rises exponentially, so that a 7.3 quake is 10 times more powerful than a 6.3 earthquake, and 100 times more powerful than a 5.3 earthquake. Theoretically, at least, there is no upper limit for an earthquake, nor, come to that, a lower limit. The scale is a simple measure of force, but says nothing about damage. A magnitude 7 quake happening deep in the mantle, say 650 kilometers down, might cause no surface damage at all, while a significantly smaller one happening just 6 or 7 kilometers under the surface could wreak widespread devastation. Much, too, depends on the nature of the subsoil, the quake's duration, the frequency and severity of aftershocks, and the physical setting of the affected area. All this means that the most fearsome quakes are not necessarily the most forceful, though force obviously counts for a lot. The largest earthquake since the scale's invention was, depending on which source you credit, either one centered on Prince William Sound in Alaska in March 1964, which measured 9.2 on the Richter scale, or one in the Pacific Ocean off the coast of Chile in 1960, which was initially logged at 8.6 magnitude, but later revised upwards by some authorities, including the U.S. Geological Survey, to a truly grand scale 9.5. As you will gather from this, measuring earthquakes is not always an exact science, particularly when it involves interpreting readings from remote locations. At all events, both quakes were whopping. The 1960 quake not only caused widespread damage across coastal South America, but also set off a giant tsunami that rolled nearly 10,000 kilometers across the Pacific and swept away much of downtown Hilo, Hawaii, destroying 500 buildings and killing 60 people. Similar wave surges claimed yet more victims as far away as Japan and the Philippines. For pure focused devastation, however, probably the most intense earthquake in recorded history was one that struck and essentially shook to pieces Lisbon, Portugal on All Saints' Day, 1st of November 1755. Just before 10 in the morning, the city was hit by a sudden sideways lurch now estimated at magnitude 9.0 and shaken ferociously for 7 full minutes. When at last the motion ceased, survivors enjoyed just 3 minutes of calm before a second shock came, only slightly less severe than the first. A third and final shock followed. The convulsive force was so great that the water rushed out of the city's harbor and returned in a wave over 15 meters high, adding to the destruction. At the end of it all, 60,000 people were dead and virtually every building for miles reduced to rubble. The San Francisco earthquake of 1906, for comparison, measured an estimated 7.8 on the Richter scale and lasted less than 30 seconds. Earthquakes are fairly common. Every day on average, somewhere in the world there are two of magnitude 2.0 or greater. That's enough to give anyone nearby a pretty good jolt, although they tend to cluster in certain places, notably around the rim of the Pacific. They can occur almost anywhere. In the United States, only Florida, eastern Texas, and the upper Midwest seem, so far, to be almost entirely immune. New England has had two quakes of magnitude 6.0 or greater in the last 200 years. In April 2002, the region experienced a 5.1 magnitude shaking in a quake near Lake Champlain on the New York-Vermont border, causing extensive local damage, and I can attest knocking pictures from walls and children from beds as far away as New Hampshire. The most common types of earthquakes are those where two plates meet, as in California along the San Andreas Fault. As the plates push against each other, pressures build up until one or the other gives away. In general, the longer the interval between quakes, the greater the pent-up pressure, and thus the greater the scope for a really big jolt. This is a particular worry for Tokyo, which Bill McGuire, a hazard specialist at University College London, describes as the city waiting to die, not a motto you will find on many tourism leaflets. Tokyo stands on the meeting point of three tectonic plates in a country already well known for its seismic instability. In 1995, as you will remember, the city of Kobe, nearly 500 kilometers to the west, was struck by a magnitude 7.2 quake, which killed 6,394 people. The damage was estimated at $99 billion, but that was as nothing, well, as comparatively little compared with what many await Tokyo. Tokyo has already suffered one of the most devastating earthquakes in modern times. On 1st September 1923, just before midday, the city was hit by what is known as the Great Kanto Quake, an event over 10 times as powerful as Kobe's earthquake. 200,000 people were killed. Since that time, Tokyo has been utterly quiet, so the strain beneath the surface has been building for 80 years. Eventually, it is bound to snap. In 1923, Tokyo had a population of about 3 million. Today, it is approaching 30 million. Nobody cares to guess how many people might die, but the potential economic cost has been put as high as $7 trillion. Even more unnerving, because they are less well understood and capable of occurring anywhere at any time, are the rarer shakings of the type known as interplate quakes. These happen away from plate boundaries, which makes them wholly unpredictable. And because they come from a much greater depth, they tend to propagate over much wider areas. The most notorious such quakes ever to hit the United States were a series of three in New Madrid, Missouri, in the winter of 1811 to 12. The adventure started just after midnight on 16 December, when people were awakened first by the noise of panicking farm animals. The restiveness of animals before quakes is not an old wives' tale, but it is but is in fact well established, though not at all understood. And then, by an almighty rupturing noise from deep within the earth, emerging from their houses, locals found the land rolling in waves up to a meter high and opening up in fissures several meters deep. A strong smell of sulfur filled the air. The shaking lasted for 4 minutes, with the usual devastating effects to property. Among the witnesses was the artist John James Audubon, who happened to be in the area. The quake radiated outwards with such force that it knocked down chimneys in Cincinnati over 600 kilometers away and, according to at least one account, wrecked boats in East Coast harbors and even collapsed scaffolding erected around the Capitol building in Washington, D.C. On 23rd January and 4th of February, further quakes of similar magnitude followed. New Madrid has been silent ever since, but not surprisingly, since such episodes have never been known to happen in the same place twice. As far as we know, they are as random as lightning. The next one could be under Chicago or Paris or Kinshasa. No one can even begin to guess. And what causes these massive interplate rupturings? Something deep within the earth. More than that, we don't know. By the 1960s, scientists had grown sufficiently frustrated by how little they understood of the Earth's interior that they decided to try to do something about it. Specifically, they got the idea to drill through the ocean floor. The continental crust was too thick to the Moho discontinuity and to extract a piece of the Earth's mantle for examination at leisure. The thinking was that if they could understand the nature of the rocks inside the Earth, they might begin to understand how they interacted, and thus possibly be able to predict earthquakes and other unwelcome events. The project became known, all but inevitably, as the Mohole, and it was pretty well disastrous. The hope was to lower a drill through over 4,000 meters of Pacific Ocean water off the coast of Mexico and drill some 5,000 meters through relatively thin crustal rock. Drilling from a ship in open waters is, in the words of one oceanographer, like trying to drill a hole in the sidewalks of New York from atop the Empire State Building using a strand of spaghetti. Every attempt ended in failure. The deepest they penetrated was only about 180 meters. The Moe Hole became known as the No Hole. In 1966, exasperated with ever-rising cost and no results, Congress killed the project. 4 years later, Soviet scientists decided to try their luck on dry land. They chose a spot on Russia's Kola Peninsula, near the Finnish border, and set to work with the hope of drilling to a depth of 15 kilometers. The work proved harder than expected, but the Soviets were commendably persistent. When at last they gave up, 19 years later, they had drilled to a depth of 12,262 meters. Bearing in mind that the crust of the Earth represents only about 0.3% of the planet's volume and that the Kola hole had no cut even one-third of the way through the crust, we can hardly claim to have conquered the interior. Even though the hole was modest, nearly everything about what it revealed surprised the researchers. Seismic wave studies had led the scientists to predict, and pretty confidently, that they would encounter sedimentary rock to a depth of 4,700 meters, followed by granite for the next 2,300 meters, and basalt from there on down. In the event, the sedimentary layer was 50% deeper than expected, and the basaltic layer was never found at all. Moreover, the world down there was far warmer than anyone had expected, with a temperature at 10,000 meters of 180 degrees Celsius, nearly twice the forecast level. Most surprising of all was that the rock at depth was saturated with water, something that had not been thought possible. Because we can't see into the earth, we have to use other techniques, which mostly involve reading waves as they travel through the interior to find out what is there. We know a little bit about the mantle from what are known as kimberlite pipes, where diamonds are formed. What happens is that deep in the earth there is an explosion that fires, in effect, a cannonball of magma to the surface at supersonic speeds. It is a totally random event. A kimberlite pipe could explode in your back garden as you read this, because they come up from such depths, up to 200 kilometers down. Kimberlite pipes bring up all kinds of things not normally found on or near the surface. A rock called peridotite, crystals of olivine, and, just occasionally, in about one pipe in 100, diamonds. Lots of carbon comes up with kimberlite ejecta, but most is vaporized or turns to graphite. Only occasionally does a hunk of it shoot up at just the right speed and cool down with the necessary swiftness to become a diamond. It was such a pipe that made South Africa the most productive diamond mining country in the world. But there may be others even bigger that we don't know about. Geologists know that somewhere in the vicinity of northeastern Indiana there is evidence of a pipe or group of pipes that may be truly colossal. Diamonds up to 20 carats or more have been found at scattered sites throughout the region, but no one has ever found the source. As John McPhee notes, it may be buried under glacially deposited soil, like the Manson crater in Iowa, or under the Great Lakes. So, how much do we know about what's inside the Earth? Very little. Scientists are generally agreed that the world beneath us is composed of four layers: a rocky outer crust, a mantle of hot, viscous rock, a liquid outer core, and a solid inner core. We know that the surface is dominated by silicates, which are relatively light and not heavy enough to account for the planet's overall density. Therefore, there must be heavier stuff inside. We know that to generate our magnetic field somewhere in the interior, there must be a magnetic there must be a concentrated belt of metallic elements in a liquid state. That much is universally accepted. Almost everything beyond that, how the layers interact, what causes them to behave in the way they do, what they will do at any time in the future, is a matter of at least some uncertainty, and generally quite a lot of uncertainty. Even the one part of it we can see, the crust, is a matter of some fairly strident debate. Nearly all geology texts tell you that continental crust is 5 to 10 kilometers thick under the oceans, about 40 kilometers thick under the continents, and 65 to 95 kilometers thick under big mountain chains. But there are many puzzling variabilities within these generalizations. The crust beneath the Sierra Nevada mountains, for instance, is only about 30 to 40 kilometers thick, and no one knows why. By all the laws of geophysics, the Sierra Nevadas should be sinking, as if into quicksand. Some people think they may be. How and when the Earth got its crust are questions that divide geologists into two broad camps: those who think it happened abruptly, early in the Earth's history, and those who think it happened gradually and rather later. Strength of feeling runs deep on such matters. Richard Armstrong of Yale proposed an early burst theory in the 1960s, then spent the rest of his career fighting those who did not agree with him. He died of cancer in 1991, but shortly before his death, he lashed out at his critics in a polemic in an Australian earth science journal that charged them with perpetuating myths. According to a report in Earth magazine in 1998, he died a bitter man, reported a colleague. The crust and part of the outer mantle together are called the lithosphere, from the Greek lithos meaning stone, which in turn floats on top of a layer of softer rock called the asthenosphere, from Greek words meaning without strength. But such terms are never entirely satisfactory. To say that the lithosphere floats on top of the asthenosphere suggests a degree of easy buoyancy that isn't quite right. Similarly, it is misleading to think of the rocks as flowing in anything like the way we think of materials flowing on the surface. The rocks are viscous, but only in the same way that glass is. It may not look it, but all the glass on earth is flowing downwards under the relentless drag of gravity. Remove a pane of really old glass from the window of a European cathedral, and it will be noticeably thicker at the bottom than at the top. That is the sort of flow we are talking about. The hour and the hour hand on a clock moves about 10,000 times faster than the flowing rocks of the mantle. The movements occur not just laterally, as the Earth's plates move across the surface, but up and down too, as rocks rise and fall under the churning process known as convection. Convection as a process was first deduced by the eccentric Count von Rumford at the end of the 18th century. 60 years later, an English vicar named Osmond Fisher presciently suggested that the Earth's interior might well be fluid enough for the contents to move about, but that idea took a very long time to gain support. In about 1970, when geophysicists realized just how much turmoil was going on down there, it came as a considerable shock. As Shauna Vogel put it in the book Naked Earth, The New Geophysics, it was as if scientists had spent decades figuring out the layers of the Earth's atmosphere, troposphere, stratosphere, and so forth, and then had suddenly found out about wind. How deep the convection process goes has been a matter of controversy ever since. Some say it begins 650 kilometers down, others more than 3,000 kilometers below us. The problem, as James Travel has observed, is that there are two sets of data from two different disciplines that cannot be reconciled. Geochemists say that certain elements on the planet's surface cannot have come from the upper mantle, but must have come from deeper within the earth. Therefore, the materials in the upper and lower mantle must at least occasionally mix. Seismologists insist that there is no evidence to support such a thesis, so all that can be said is that at some slightly indeterminate point as we head towards the center of the earth, we leave the asthenosphere and plunge into pure mantle. Considering that it accounts for 82% of the Earth's volume and 65% of its mass, the mantle doesn't attract a great deal of attention, largely because the things that interest Earth scientists and general readers alike happen either deeper down, as with magnetism, or nearer the surface, as with earthquakes. We know that to a depth of about 150 kilometers, the mantle consists predominantly of a type of rock known as peridotite. But what fills the next 2,650 kilometers is uncertain. According to a Nature report, it seems not to be peridotite. More than this, we do not know. Beneath the mantle are the two cores, a solid inner core and a liquid outer one. Needless to say, our understanding of the nature of these cores is indirect, but scientists can make some reasonable assumptions. They know that the pressures at the center of the Earth are sufficiently high, something over 3 million times those found at the surface, to turn any rock there solid. They also know from the Earth's history, among other clues, that the inner core is very good at retaining its heat, although it is little more than a guess. It is thought that in over 4 billion years the temperature at the core has fallen by no more than 110 degrees Celsius. No one knows exactly how hot the Earth's core is, but estimates range from something over 4,000 degrees to over 7,000 degrees Celsius, about as hot as the surface of the sun. The outer core is in many ways even less well understood, though everyone is in agreement that it is fluid and that it is the seat of magnetism. The theory was put forward by E. C. Bullard of Cambridge University in 1949 that this fluid part of the Earth's core revolves in a way that makes it, in an electrical motor, creating the Earth's magnetic field. The assumption is that the convecting fluids in the Earth act somehow like the currents in wires. Exactly what happens isn't known, but it is felt pretty certain that it is connected with the core spinning and with its being liquid. Bodies that don't have a liquid core, the Moon and Mars, for instance, don't have magnetism. We know that the Earth's magnetic field changes in power from time to time. During the age of the dinosaurs, it was up to 3 times as strong as it is now. We also know that it reverses itself every 500,000 years or so on average, though that average hides a huge degree of unpredictability. The last reversal was about 750,000 years ago. Sometimes it stays put for millions of years. 37 million years appears to be the longest stretch, and at other times it has reversed after as little as 20,000 years. Altogether, in the last 100 million years, it has reversed itself about 200 times, and we don't have any real idea why. This has been called the greatest unanswered question in the geological sciences. We may be going through a reversal now. The Earth's magnetic field has diminished by perhaps as much as 6% in the last century alone. Any diminution in magnetism is likely to be bad news, because magnetism, apart from holding notes to refrigerators and keeping our compasses pointing the right way, plays a vital role in keeping us alive. Space is full of dangerous cosmic rays which, in the absence of magnetic protection, would tear through our bodies, leaving much of our DNA in useless shreds. When the magnetic field is working, these rays are safely herded away from the Earth's surface and into two zones in near space called the Van Allen belts. They also interact with particles in the upper atmosphere to create the bewitching veils of light known as the auroras. A big part of the reason for our ignorance is that traditionally there has been little effort to coordinate what's happening on top of the Earth with what's going on inside it. According to Shauna Fogel, geologists and geophysicists rarely go to the same meetings or collaborate on the same problems. Perhaps nothing better demonstrates our inadequate grasp of the dynamics of the Earth's interior than how badly we are caught out when it plays up, and it would be hard to come up with a more salutary reminder of the limitations of our understanding than the eruption of Mount St. Helens in Washington state in 1980. At that time, the lower 48 states of the Union had not seen a volcanic eruption for over 65 years. Therefore, most of the government volcanologists called in to monitor and forecast St. Helens behavior had seen only Hawaiian volcanoes in action, and they, it turned out, were not the same thing at all. St. Helens started its ominous rumblings on 20th of March. Within a week, it was erupting magma, albeit in modest amounts, up to 100 times a day, and being constantly shaken with earthquakes. People were evacuated to what was assumed to be a safe distance of 13 kilometers. As the mountain's rumblings grew, St. Helens became a tourist attraction for the world. Newspapers gave daily reports on the best places to get a view. Television crews repeatedly flew in helicopters to the summit, and people were even seen climbing over the mountain. On one day, more than 70 copters and light aircraft circled the peak. But as the days passed and the rumblings failed to develop into anything dramatic, people grew restless, and the view became general that the volcano wasn't going to blow after all. On 19th of April, the northern flank of the mountain began to bulge conspicuously. Remarkably, no one in a position of responsibility saw that this strongly signaled a lateral blast. The seismologists resolutely based their conclusion on the behavior of Hawaiian volcanoes, which don't blow out sideways. Almost the only person who believed that something really bad might happen was Jack Hyde, a geology professor at the community college in Tacoma. He pointed out that St. Helens didn't have an open vent, as Hawaiian volcanoes have. So any pressure building up inside was bound to be released dramatically and probably catastrophically. However, Hyde was not part of the official team, and his observations attracted little notice. We all know what happened next. At 8:32 a.m. on a Sunday morning, 18th of May, the north side of the volcano collapsed, sending an enormous avalanche of dirt and rock rushing down the mountain slope at nearly 250 kilometers an hour. It was the biggest landslide in human history and carried enough material to bury the whole of Manhattan to a depth of 120 meters. A minute later, its flank severely weakened. St. Helens exploded with the force of 27,000 Hiroshima-sized atomic bombs, shooting out a murderous hot cloud at up to 1,050 kilometers an hour, much too fast, clearly, for anyone nearby to outrace it. Many people who were thought to be in safe areas, often far out of sight of the volcano, were overtaken. 57 people were killed. 23 of the bodies were never found. The toll would have been much higher had it not been a Sunday. On any weekdays, many lumber workers would have been working within the death zone. As it was, people were killed 30 kilometers away. The luckiest person on that day was a graduate student named Harry Glicken. He had been manning an observation post 9 kilometers from the mountain, but he had a college placement interview on 18th of May in California, and so had left the site the day before the eruption. His place was taken by David Johnston. Johnston was the first to report the volcano exploding. Moments later, he was dead. His body was never found. Glicken's luck, alas, was temporary. 11 years later, he was one of 43 scientists and journalists fatally caught up in a lethal outpouring of superheated ash, gases, and molten rock, what is known as a pyroclastic flow, at Mount Unzen in Japan, when yet another volcano was catastrophically misread. Volcanologists may or may not be the worst scientists in the world at making predictions, but they are without question the worst in the world at realizing how bad their predictions are. Less than 2 years after the Unzen catastrophe, another group of volcano watchers, led by Stanley Williams of the University of Arizona, descended into the rim of an active volcano called Galeras in Colombia. Despite the deaths of recent years, only two of the 16 members of Williams' party wore safety helmets or other protective gear. the volcano erupted, killing six of the scientists, along with three tourists who had followed them, and seriously injuring several others, including Williams himself. In an extraordinarily unself-critical book called Surviving Galeras, Williams said he could only shake my head in wonder when he learned afterwards that his colleagues in the world of volcanology had suggested that he had overlooked or disregarded important seismic signals and behaved recklessly. How easy it is to snipe after the fact, to apply the knowledge we have now to the events of 1993, he wrote. He was guilty of nothing worse, he believed, than unlucky timing when Galeras behaved capriciously as natural forces are wont to do. I was fooled, and for that I will take responsibility. But I do not feel guilty about the deaths of my colleagues. There is no guilt. There was only an eruption. But to return to Washington, Mount St. Helens lost 400 meters of peak, and 600 square kilometers of forests were devastated. Enough trees to build 150,000 homes, or 300,000 according to some reports, were blown away. The damage was placed at $2.7 billion. A giant column of smoke and ash rose to a height of 18,000 meters in less than 10 minutes. An airliner some for 80 kilometers away reported being pelted with rocks. 90 minutes after the blast, ash began to rain down on Yakima, Washington, a community of 50,000 people about 130 kilometers away. As you would expect, the ash turned day to night and got into everything, clogging motors, generators, and electrical switching equipment, choking pedestrians, blocking filtration systems, and generally bringing things to a halt. The airport shut down and highways in and out of the city were closed. All this was happening, you will note, just downwind of a volcano that had been rumbling menacingly for 2 months. Yet, Yakima had no volcano emergency procedures. The city's emergency broadcast system, which was supposed to swing into action during a crisis, did not go on the air because the Sunday morning staff did not know how to operate the equipment. For 3 days, Yakima was paralyzed and cut off from the world. Its airport closed, its approach roads impassable. Altogether, the city received just over 1.5 centimeters of ash after the eruption of Mount St. Helens. Now bear that in mind, please, as we consider what a Yellowstone blast would do.